Hi everyone, this is Scott Sullivan, and today I'll be doing a presentation on latent Dirichlet allocation, specifically regarding the algorithm description. LDA is primarily concerned with topic modeling in text. So humans are good at understanding topics in a document. We understand what it means to play baseball, we understand how to follow a cooking recipe, we understand what kind of emotions are conveyed via text. We can detect context, pick up on similarities, and extract meaning, and we can do this all very easily. Machines have a much harder time with this. So LDA focuses on trying to solve this problem by topic modeling, which is creating a type of statistical model for discovering the abstract topics that occur in a collection of documents. This was originally proposed by Bly et al. In 2003. LDA is typically used to detect underlying topics in text documents, but there are other applications such as sentiment analysis, object localization for images, automatic harmonic analysis for music, bioinformatics, etc. However, the focus of this presentation will be on LDA's traditional use case, which is detecting underlying topics across a corpus of text documents. So this slide will kind of talk about some of the description of the assumptions and a little bit of the terminology in LDA. LDA suggests that words carry strong semantic information, and documents discussing similar topics will use a similar group of words. Latent topics are therefore discovered by identifying groups of words in the corpus that frequently occur together within documents. The second fundamental assumption that LDA makes is concerning the structure of the documents themselves. LDA suggests that documents are probability distributions over latent topics, and topics are probability distributions over words. This means that according to LDA, every document contains a number of topics. Each topic has a distribution of words associated with it. The important aspect here is that we'll be working with probability distributions rather than strict word frequencies. So while other bag of words models may focus on the most frequently occurring words in a document, we'll be taking a more holistic approach by concentrating on the distribution of words across topics. And then the following documents, or the images, you can see several documents are comprised of a distribution of topics, and are described by a distribution of words. So this slide will be talking about plate notation. Plate notation is a concise way of visually representing the dependencies among the model parameters. If you look at the larger rectangle denoted by M, that indicates the total number of documents within the corpus. And the smaller rectangle N denotes the number of words in a document. So all of the parameters, depending on where they fall inside of those two rectangles, that indicates whether they apply at the document level, at the word level, or at both. So you can see that two parameters exist outside of the rectangles, alpha and beta. Those are called the Dirichlet priors. Alpha is the parameter of the Dirichlet prior on the per document topic distributions. A high alpha indicates that each document is likely to contain a mixture of most of the topics, and not just one or two in particular. Conversely, a low alpha says that each document will likely contain just a few of the topics. Beta is the parameter of the Dirichlet prior on the per topic word distribution. A high beta indicates that each topic will contain a mixture of most of the words. Low beta says that each topic may contain a mixture of just a few of the words. Theta is the topic distribution for document M. Z is used to notate each topic, which is assigned to each word, therefore making each document a mixture of these topics, and W stands for word. And then this is just the parameters written out. So this is what we were demonstrating in the previous slide using the plate notation. So in this next slide, we'll be talking about the generative process. And LDA assumes that new documents are created in this particular way. But before I get into that, it's worth noting that this isn't actually the algorithm running. When we look at latent Dirichlet allocation, we'll actually look at this in the reverse. We'll start with documents, and we'll work our way back to what we think are good topics in those documents. But in order to understand how latent Dirichlet allocation assumes the documents are created, it's good to look at the generative process. So according to LDA, if we wanted to create a new article, the first thing that we would do would be to determine the number of words in the document. The second step that we would take would be to choose a topic mixture for the document over a fixed set of topics. So for example, 20% topic A, 30% topic B, 50% topic C. The third step would be to generate the words in the document by first picking a topic based on the document's multinomial distribution above, and that's that 20%, 30%, 50%. And then the second step would be to pick a word based on the topic's multinomial distribution, their own distribution. And so we would iterate through this until we reach that number of words that we had specified. So basically, words are selected from topic buckets based on how much each topic will occur in the document. The words are mixed together, and then that's the new document that's created. So here's a quick example of that generative process. Say we have a group of articles, and we assume that all of these articles can be characterized by 3 topics: animals, cooking, and politics. Each of those topics can be described by the following words. Animals can be described by dog, chicken, cat, nature, and zoo. Cooking by oven, food, restaurant plates, taste, and delicious. And politics can be described by distribution of Republican, Democrat, Congress, ineffective, and divisive. So say we want to generate a new document that is 80% about animals and 20% about cooking. We would choose the length of the article, say 1,000 words. Then we would choose a topic based on our specified mixture. So out of our 1,000 words, roughly 800 will come from the topic animals and roughly 200 will come from the topic cooking. And then the third and final step is we would choose a word based on the word distribution for each topic. So all of these words that we have randomly selected would become the new article. This is how LDA assumes that articles are created. Syntax doesn't really matter to the model, only the distribution of words. So while we would never be able to read this document, we could at least understand that this article is about cooking and animals, not about politics. This is a demonstration of what an LDA model assumes to be true. In reality, we'll work backwards from this point, although the principle remains the same. So this is the working backwards step. Suppose you have a corpus of documents. You want LDA to learn the topic representation of K topics in each document and the word distribution of each topic. LDA backtracks from the document level to identify these topics that are likely to have generated the corpus. So this is the process. 1, we'll randomly assign each word in the document to one of K topics. For each document D, assume that all topic assignments except for the current one are correct. Calculate 2 proportions. 1, the proportion of words in a document D that are currently assigned to topic T, and that's this formula here. And then 2, proportion of assignments to topic T over all documents that come from this word W, and that's the equation there. You'll multiply these 2 proportions, and you'll assign W a new topic based on that probability. So according to our generative model, this is essentially the probability that topic T generated word W. So it makes sense that we would resample the current word's topic with this probability. In other words, we're assuming that all the topics assignments except for the current word in question are correct. And then we're updating the assignment of the current word using our model of how documents are created. And then eventually we'll reach a steady state where the assignments make sense. So now we have the topic mixtures of each of our documents and the underlying word distributions as well. It's important to note that while we can manually add human readable labels to these various topics, that isn't necessarily the point of LDA, nor is it necessary. So in fact, we can calculate similarities between articles without ever assigning labels to our topics. In conclusion, according to latent Dirichlet allocation, documents are probability distributions over latent topics. Topics are then probability distributions over words. LDA takes a number of documents. It assumes that the words in each of the document are related. It then tries to figure out the recipe for how each document could have been created. We just need to tell the model how many topics to construct, and it uses that recipe to generate topic and word distributions over a corpus. Based on that output, we can identify similar documents within the corpus. Some of the advantages of LDA are that it's an effective tool for topic modeling. Conceptually, it's fairly easy to understand and has been shown to produce good results over many domains. There's also new applications every day for LDA. Some of the limitations are that you must know the number of topics K in advance, and this can be tricky to determine or require a lot of trial and error. And secondly, Dirichlet topic distributions cannot capture correlations among topics, and so that's something to consider, that you may have multiple correlated topics. Well, I hope that you all enjoyed my presentation, and thank you.